All right. Hello. Hello, hello. Welcome. We are here to do more physics C mechanics work today. Welcome. Today we are going to be talking about, oh, Kristen is here, ready to go. Hi, Kristen. As you're coming in, definitely feel free to drop a hello in the chat to let us know you're here. But wonderful, welcome. Today we're gonna do kind of a couple of different topics from a couple of different units. The theme that they have in common is that it's everything that's going in a circle. So this cram and the next cram are both going to be talking about rotation. So objects traveling in a circle. And we had to kind of split it up because there's so much awesome content that we needed to do it in 2 crams. So we'll give everyone just another 30 seconds or so to jump on. If you are here, welcome. Grab some scratch paper, grab a calculator. I've got some multiple choice problems for practice for you at the first half of the cram, and then we're going to do a free response in the second half. So like I said, if you're just coming in, welcome. We're doing rotation today. It's the first of 2 crams that we're going to talk about things going in a circle. So we will get started in just a moment. Feel free to drop a hello in the chat. We've got some folks with us already saying hi. It's great to be with you all, and I am looking forward to this one and the next cram. I very much enjoy talking about things going in a circle. It's a lot of fun. So we should get rolling. So a couple just logistical things as always before we start. First one, we are recording this, right? So kind of the standard disclaimer here might appear on Fiveable's website, YouTube, other public spaces. So if you are asking a question in the chat, your name might appear. So make sure that you use the name that you want to be associated with this. Also, always a plug to follow Fiveable on all of the social medias. So Twitter, Instagram, YouTube, @ThinkFiveable. A lot of great content out there. I know we're continuing to gear up. APs are right around the corner, right? So they've got a lot of great content posted pretty much daily. So if you haven't yet followed, please do. All right, so we've got 3 big topics in this stream today. The first one, we are going to talk about rotational kinematics. So that's just going to be a lot of some vocab and some just kind of like language conversations about what happens when we look at things going in a circle. We're going to spend a lot of time in our hour today talking about uniform circular motion. This is actually a Unit 2 topic technically, but I saved it until now because for me, it just makes sense. Everything going in a circle should just go together. So we're going to talk about it now for quite a while. And then in the last part of the cram today, we'll talk about rotational energy and how we approach things that are not only moving translationally or linearly, but also when they're rotating at the same time. So that is the plan. As always, if you have questions or comments or anything, definitely stick them in the chat. I am here. Kristen is here to help, and we're really just here for you to do anything answer any questions that you have and help any way we can. All right, so first section here is rotational kinematics. So 3 key ideas. The first one is just talking about rotational motion. We're going to talk about what the right-hand rule is. This is the first time in this cram series where the right-hand rule has come up. It will come up again in future crams. So I wanted to really spend a couple minutes just talking about it and how to do it. And then we'll talk about rotational kinematics specifically. So first thing, as I said, this first part is really just kind of talking a little bit about language and notation when things happen in a circle. So we've got 2 types of motion now. We've got translational motion, which is things traveling linearly, whether that's in 1 dimension or 2 dimensions, but it's in a straight line, or actually not even a straight line, but moving linearly or translationally. And then there's this angular motion or rotational motion when things are spinning. And there's really kind of the theme for this cram and the next cram is going to be that all of the things we've already talked about in physics have a rotational counterpart, and they function pretty much the same way. It's just being able to translate between talking about it in a translational moment versus talking about it in a rotational moment. So our kinematics values are the first example of that. So in previous crams, specifically in like the first one, we talk about displacement, velocity, acceleration. We symbolize displacement as x or s. Sometimes you'll even see it as r. Velocity is v and acceleration is a. And our units there are always like meters and some combination of meters and seconds, right? In the angular rotational world, we have those same ideas, just they are in, we have to talk about it in terms of things rotating. So instead of meters, we use radians typically. We symbolize displacement with the Greek symbol theta. So we think about it in terms of like the angle, right? And we measure angles in radians. Velocity, we talk about something called angular velocity, and we symbolize it with this omega right here, radians per second. And then acceleration is alpha. Alpha is easy, right? Because it starts with an A. So I think of alpha for acceleration. It kind of even looks like an A a little bit, right? Just like omega, kind of like, I know it looks more like a W than a V, but it kind of looks like a V. That's how you can kind of remember it. And it's acceleration is radians per second squared. So basically all of the meters turn into radians because we're now measuring the displacement in a circle instead of in a, straight translationally. And there's a formula. There's a formula to convert each of these different values between the translational and the angular values, and it's the same thing. It's the same idea. It's just depending on what you're looking at. So if we're looking at displacement, linear displacement is equal to the radius of whatever circle times the angular displacement. Linear velocity is equal to the radius times the angular velocity. Acceleration, linear acceleration is equal to the radius times the angular acceleration. So this is, hopefully you can see there's kind of a pattern here, right? To translate from the linear to the angular, we multiply whatever the angular thing is times the radius. I put a note here. The only one of these formulas that's actually on your equation sheet is this second one, the velocity one. But it's nice that you have that because you can see that the trend is the same no matter which one you're looking for. So you've got this as kind of your reference, and then you know that if we want acceleration, instead of having v and omega, we just have a and alpha, if that makes sense. So these are our different rotational motion variables, and we're gonna, as I said, keep seeing this theme where we've got the same ideas as what we've been talking about. There's just like a different label for them when they happen in a circle. We also have to talk about direction. So direction gets a little trickier when we're going in a circle because if we're going in a circle, our linear or our translational direction is kind of always changing, right? So we have to talk about direction in rotation. And the way that we figure it out is we do something called the right-hand rule. So I will confess the right-hand rule took me longer to understand than it should have. I think it can be confusing, and so I wanted to spend a moment to just maybe say it in a different way than you've heard from others in the past, or refresh just to make sure in case folks are kind of confused by it. So first step is to use your right hand, and that can be a challenge in itself, so just remember which one's your right hand. That's the first one. And then some folks like to do the three-fingered one, and they point in different directions. For me, that can be a little confusing. So all I think about is what I want to do when I'm using my right hand is I'm going to curl my fingers in the direction of the rotation. So if we're looking at this picture up here at top right, we can see that the rotation of this wheel is going up like this. And so the hand is curving, the four fingers are curving in that direction of the rotation. And then the reason that we do that is because your thumb will point in the direction of the vector. So you can see that the fingers are curving, and then the thumb is pointing out, and the thumb is pointing in the direction of that angular velocity vector. So we'll use the right-hand rule for a variety of different things in the next couple of crams. So it's important to know because it will, the test will ask you, like, is it pointing into the paper or out of the paper or what's going on? And so the way we figure it out is we just curl our fingers in the direction of the rotation, and then your thumb points in the direction of the vector. So if you wanted to just take a second and think about what direction the angular velocity vector points. We've got this cat spinning on a Roomba here. So the way we would do it, right, is we would take our right hand, we take our fingers. You can't see me, but I'm like doing it right now, right? So I'm curling, and my thumb is pointing down. So my angular velocity vector in that case is going to be pointing down. Great. Okay, and so then the last part of this first section is the actual rotational kinematics equations. So if we look at them, we can see that all we're doing for the rotational kinematics equations here is we're taking the translational ones, the symbols, so V sub x, V naught, A, T, and we're just plugging in the equivalent angular notation. So instead of your linear or your translational velocity, you've got your angular velocity. Instead of your translational acceleration, you've got your angular acceleration. In the second one down here, instead of your translational displacement, you've got your angular displacement. So all we're doing, it's the same thing that you've already been doing with the regular kinematics equations and regular kinematics problems. It's just we're doing it in angular values. So instead of in meters, we're in radians, and we're talking about things spinning. I also wanted to point out that while the first two of these are on your equation sheet, I don't know why, but the third one isn't. The linear one is, the translational one is, but the angular one isn't. You treat it the same way. All you need to do is plug in anywhere you see a V, you plug in an omega. Anywhere you see an A, it's an alpha, and X's become thetas. But that last one isn't on your equation sheet, but it is, I'm blanking on the word. It's valid. That's the word I was looking for. It's totally valid if you want to use it. You would just translate your linear one into this guy. So that's it. So that's rotational kinematics. I think I have a practice problem here. So all this practice problem is going to ask you is to translate the ideas between your linear values. So this one actually asks about momentum. Translate from your linear values to some angular values, just remembering the relationships between linear and angular motion variables. So hopefully you're already working on it. If you're not, work on it now. I'll give you 30 seconds or so. I'll open up a poll to see what we've come up with. And let's see what you can do. When you're ready, go ahead and choose an answer. Take another, 10 seconds or so. All right, great. Yeah, y'all got it. Wonderful. Good work. You are champs. So correct response was A here. We all got it right. Good work. If we look at my explanation, it is here for you. We know that mass is just m, the radius is r, and then we know angular velocity is omega, and we just convert the idea of linear momentum, p equals m times v, and then this formula that will let us translate between linear velocity and angular velocity. Just plug it in, and we should get A. Cool. Okay, so we are going to spend a good amount of the next part of the Cram talking about UCM, uniform circular motion, because there's a lot of kind of nitty-gritty pieces to this that I want to just make sure that we talk about so that way you're in good shape for the test. So 2 key ideas. The first thing we're going to talk about for a while is centripetal acceleration and centripetal force. Then we are going to talk about a couple of special cases that we come across in uniform circular motion that I want to just say so that way when you come across something like it, you know kind of the tricks and the tips that go with it. So the first thing, what is uniform circular motion? Uniform circular motion is the name we give to the situation when we've got an object that's moving at a constant speed on a circular path. So you've got an example on your screen. We've got an object, it's moving in a circle, and its speed is the same. Note that I'm very intentionally saying that the speed is constant because the velocity of that object is very much not constant because its direction is changing, right? If you're going in a circle, your direction is constantly changing. So your velocity vector is not constant, but the magnitude of it, your speed, right, how fast you're going, is constant. So by definition, uniform circular motion, the object is moving at a constant speed. When we're looking at this, when we're talking about speed and velocity, the speed is constant, but the velocity vector, as I said, is changing. Again, by rule, the velocity vector is always going to point tangent to the path. So remember that tangent means one intersection point on the circle, right? So you can see this velocity vector here in this animation. It's pointing, as the object's going around, it's pointing in the direction the object's going, and it's pointing tangent to that path. If we were to cut the string or somehow get rid of the object's circular motion, the object is always going to travel in a tangent to the circle that it's going in. So it would keep going in a straight line along that velocity vector arrow as it goes around. Cool. For uniform circular motion, also important to note that there is a net force always because it's got to go in a circle, right? And then there's always an acceleration because if there's a net force, there has to be an acceleration. And we'll talk about what both of those are in a moment. Okay, so first, before we get too far into force and acceleration, let's just talk about that velocity vector and do one practice problem with it. So here we've got another problem. We've got a compressed spring mounted on a disc that can project a small ball. We can see the picture here that when the object the disc is not rotating, the velocity vector goes straight out. The disc is going to rotate in a counterclockwise direction. As seen from above, the ball is projected outward. Which of the following best shows the subsequent path of the ball relative to the ground? So you've got 5 choices. Because I only can ever have 4 answers this time, chose B, C, D, or E. So A is not right. But I will open this up and see what you all think about this one. See what you can come up with for that. What path will the ball take? Take another 10 seconds or so. All right, I think we're split on this one. So let me show you. Some of us said C, some of us said E. E is the correct answer, and let's talk about it. So I drew some pictures for you. If we look at the disc, it's rotating counterclockwise. So it's rotating like this. And there's 2 velocity vectors that we have to deal with. The velocity that's from the spring, putting it directly outward. And then there's also the velocity, because it's moving in a circle, there's going to be that velocity vector that's tangent to the path. So if it's moving like this, Then at this point, the velocity vector from the uniform circular motion points in this direction. From here, we're going to use head to tail method, right, to add our vectors to find the final direction. So if we take a look, we've got the velocity from the spring, the velocity from the circle, and so our resultant vector points in this direction, which ends up being E. If y'all have questions about that, definitely stick them in the chat. Yeah, you are already doing that. That's awesome. Okay, cool. So let's talk about centripetal acceleration and force. So anytime an object is moving in uniform circular motion, it will have both of these things. The object is accelerating only because it's changing direction. So we know when an object is accelerating, it's changing its velocity, right? And we know that if it's moving in uniform circular motion, then the only part of its velocity that's changing is its direction. And so because of that, the acceleration of the object is also only changing direction. And there's a formula that we can use to calculate it. It's on your equation sheet. We symbolize centripetal acceleration A sub c, and we can get a number for it, and it's equal to the velocity of the object squared over the radius of the circle, which is equal to the angular velocity squared times the radius. Those you could just plug in one velocity, that the relationship between the linear and angular velocity to go between those. So when we're finding that centripetal acceleration, this is the formula that we use. That acceleration is caused by centripetal force. So we symbolize centripetal force F sub c. And the centripetal force is just the special name that we give to the force that causes an object to move in a circle. So this is I want to just if you hear anything from me today about any of this, this is the thing I want you to hear. Centripetal force isn't a special force. As you're looking at a situation, it's not like you're going to be like, okay, there's weight and normal force, and then there's centripetal force, and it's the special extra force. That is not true. Centripetal force is just an extra name that we give to the forces that are already in the problem, and it's the force that's causing the object to move in a circle. So sometimes the centripetal force is going to be tension. If an object is getting swung around on a rope in a circle, the rope is the thing causing it to go in a circle. So the tension in the rope is the centripetal force. Sometimes it could be normal force. So if you've got a marble on doing a loop-de-loop or something like a roller coaster, right, with a loop in it, the normal force from the track is the thing causing the roller coaster cart to move in a circle. So in that case, that's the centripetal force. So it's not an extra force. It's just a special name we give to the forces that are already in the problem that you already know about. We do have an extra way to calculate it, though, because we can calculate the centripetal acceleration with this extra formula. So this formula is not on your equation sheet as it is written here, but all it is taking the net force, the Newton's second law and the net force equation, and plugging in the centripetal acceleration, right? So if we've got F equals ma, centripetal force is going to be m times your centripetal acceleration, which you've got over here. So that's one way we can calculate it. We also know that the only force acting on something moving in uniform circular motion is going to be whatever the centripetal force is. Cool. So the other part of this is that both the centripetal acceleration and the centripetal force vector, they're always going to point towards the center of the circle, because this is the forces causing it to go in a circle, and we know that the acceleration vector always points in the same direction as the net force vector. So those are both always going to point to the center of the circle. Velocity is going to be tangent up here. So this is a nice image for you to think back on as you're trying to unpack uniform circular motion. Okay, so I think I've got a bunch of practice problems now to throw at you for the next few minutes. So first one here. springs, it's got a force constant of 100 newtons per meter, unstretched length of 0.07 meters. It's going to rotate in the center of a smooth table as shown. This is the top view, right? So it's going to rotate like this. We've got a 1 kilogram disc moving in uniform circular motion. As soon as you see uniform circular motion, that's going to tell you a lot of stuff, right? That's going to tell you that the only net force is whatever's making it go in a circle. It's telling you it's moving at a constant speed, things like that. And this spring is causing a, I'm trying not to give it away, actually. We've got the spring. It's going to stretch by 0.03 meters as it's going in a circle. So your goal is to find the centripetal force on the disc. You will definitely use, think about what the centripetal force is, like not just like, is it friction, or is it tension, or is it whatever, like whatever force you think it is, and try and see if you can't figure out what that centripetal force is, and then we'll talk about it. I will open up another poll for you all. See what you can come up with. Nice, we've already got a couple of votes in. If you're still working, take another 20 seconds. Y'all are probably working while I was talking, rambling on. Okay, great. So if you're going to vote, this is your last chance. For those that have voted, y'all are looking great. Yeah, okay, good. I think we got everyone. And we got it right. Yay! Awesome. Go team. Okay, so let's just take a look just to do it. Here are some things we know. We know the spring constant. We know the unstretched length. We know the distance that it's stretched. And we know its mass. So that's a lot of info. We don't actually need all of it, because the only thing that we know is that in this case, the centripetal force is equal to the spring force. It's technically it's the opposite, right? Because of Newton's third law, but we know that we can, it's multiple choice, right? We just need to get a number. So we know that we can calculate it using our spring force equation, Hooke's law, right? Negative kx. So all we need to do is plug in our spring constant and that distance stretched as 0.03, get a number, and then if we're being real technical about it, like I said, we know that spring force is going to be equal and opposite to the centripetal force, so it's going to be equal to 3, and we'll get B. Nice. Okay, same situation here. No. Oh, there we go. Hopefully, I ruined it. Same situation here, but this time it's asking you about the work done. So see if you can take a moment and figure out what you get for there. Oh, I have to open the poll. There we go. Sorry. Nice. That was quick. That's great. Yeah, y'all got it, right? That was really just a question about work. So work done, total work done there is 0. And because the force points towards the center and the perpendicular to the distance traveled, no work is done. Great. Next one, car moving around the circular track, radius 300 meters. At the instant where the car's velocity is directed due east, acceleration is directed due south and has a magnitude of 3 meters per second squared. When viewed from above, which direction is the car moving? and what is its speed? I will open up another. There we go, opened up. So this question's probably the most thing is just kind of rating it and unpacking it and drawing a picture, right? So if you're stuck for this one, the first thing we should probably do is draw a picture just to get an idea of where those vectors are and what they're doing. Take another 20 seconds or so. I think we're waiting on a few more. All right, so we're a little split on this one, so let's take a minute and look at it. Show you what we did. So the correct answer here is A. For those that picked D, let's figure out why. So first thing we should do here is probably draw a picture, right? So we know that the car's velocity is directed east, so that's pointing towards the right, and the acceleration is directed south. So the first thing is like trying to figure out, and we know the car is moving in a circle. So the first thing to figure out is kind of like where those vectors are and how are they related to each other, right? So we know that if we're moving in a circle, then the velocity is going to be tangent to that circle. So that automatically tells us either it's going to be at the top here or it's going to be at the bottom, right? Because it's got to be tangent. And then we know that the acceleration, the centripetal acceleration, has to point towards the center. So because of that, we know that the point here is going to be at the top. The acceleration is going to point towards the center. Velocity is going to point towards the right. And if the velocity is pointing towards the right, then we must be moving in this direction. This direction is clockwise. This is harder for, I imagine you all, because it's all like, you just use digital clocks, right? So clockwise and counterclockwise, actually, I'm actually just realizing this as I'm talking to you, like is like harder than it used to be. So clockwise is in this direction. So we must be moving like this. And then to find I keep clicking, I'm sorry. To find the actual velocity, we're going to use that centripetal acceleration formula, right? So we know the acceleration is 3. We know the radius of the track, and we'll just solve for the velocity. So our answer will be A here. Reminder, as always, if you have questions, definitely. Oh, yeah. Okay, I just looked at the chat. I am super sympathetic to clockwise and counterclockwise. Oh my gosh. Yeah, I can't. I'm just old, and so I have analog clocks in my life more. Okay, sorry, sidetracked. Okay, so next one. Ball attached to a string, rolled around in a horizontal circle with a radius r. What happens if we change the radius of the circle to 4r and apply the same centripetal force? So this is a super common type of question, right? Looking at like ratios here and being able to interpret the differences. So I will open up another poll. Reminder that if we ever get stuck with a problem like this, we can always plug in numbers, right? So pick a number for the initial radius and then multiply it by 4 for the new radius and see what happens to the speed. So I'll give you a second to work on that one. All right, take another, I don't know, 10 seconds or so. I think we're missing just a couple folks. All right, let's see. Oh, there we go. Okay, cool. Yeah, y'all got it right. Good. So I will show you. It's D. Everyone got that. Good work. Go team. If we take a look at it, we know the radius changes. We know the force is the same. We know the mass is the same. So we're going to use that the Newton second law F equals ma, and we'll plug in the centripetal acceleration equation here. And then you can see all I did is rearrange the equation to solve for v, and then we can see that it's twice the speed. Again, if all of the variables get cumbersome or you're just like not feeling it, you can always plug in numbers. So I would have plugged in like 1 and then 4, right? And see what happens to the different speeds and how they relate to one another. Okay. I told you I was throwing a lot of multiple choice at you. Here's another one. I think this might be the last one. We've got mass hung vertically from a string, and the maximum amount that can be hung vertically from a string without breaking is 10 kilograms. Length of the string, 2 meters long, rotates in a circle on a frictionless table where the string is horizontal. The maximum speed the mass can attain under these conditions without the string breaking. So think about what that first sentence tells you in order to answer the question, and then the situation is really that second sentence on, right? Like that's what you're trying to figure out. So take a moment and see if you can do that one. I will open another poll. I'll give you a little longer for this one. I know it's there's a little extra calculating in this one. All right, take another 10 seconds or so. All right, let's see what we've got here. So I think some people were probably still working on that one. I apologize for going a little fast on that one, but for those that did vote, we got it right. Good work. So let's talk about it, just to be sure. So first here is kind of unpacking the problem, right? So there's actually 2 separate parts to this multiple choice problem. The first sentence tells us about the maximum mass and therefore the maximum force that can hang from the string without breaking. And we need that to be able to figure out the speed. So the first thing we'll do here is figure out, if it's hung vertically, then the force acting on the mass is going to be weight, right? So the maximum amount of force that the string can handle before it breaks is going to be the weight of that 10 kilogram mass. So it's going to be 98 newtons. So we know from that part that to figure out the maximum speed without the string breaking, the max centripetal force that the string can hold or can handle is 98 newtons. From there, I keep clicking, I'm so sorry. From there, we've got that 98 and we're going to plug it into the centripetal force equation. We know the mass is 0.5 kilograms. We know that the length of the string is 2 meters long, and we'll just solve for V. And then we see that it's like slightly different because just significant figures, right? So it's 19.79 if you calculate it using significant figures. That would be 20 if you were to use those rules. It's also multiple choice, right? So you're looking at it and you're like, that's super close. It's probably right. I think that's a totally legit way to look at that too. Great. Okay, so a couple of special cases here. First one is a vertical circle. So when we're in uniform circular motion and the path is vertical, the centripetal force calculations will get a little trickier because now we've got to take into account gravity, right? So gravity affects what's going on. And there's a couple of rules. So when the object is at the top of the motion, so if we're vertical now, instead of horizontal, we're vertical, the top of the motion, whatever the centripetal force, whatever's causing it, whether it's tension or it's normal force or whatever it is pointing in the same direction as the gravity of the object, the weight of the object, right? So those two things are going to add. When the object's at the bottom of the circle, those two things are pointing in opposite directions. So it's going to subtract from whatever force is causing your centripetal force to find your net force as you're going in uniform circular motion. So a couple of common examples that you'll see for this. This top image is talking about swinging by like a rope or something like that, a string, right? So tension is your centripetal force and you're just swinging it vertically. You'll also see like Ferris wheels and roller coasters. That's going to be normal force, but the same principles apply, right? If the centripetal force and the weight are pointing in the same direction, then your net force is going to be, you're going to add them. If they're pointing in opposite directions at the bottom of the circle, you're going to subtract the weight from whatever your centripetal force is going to be. So we're going to do one practice with this. I'll talk about one more special case, and then we're going to talk about energy. So here's one more practice. This one, most of the ones that I use come from old tests. This one I just wrote. I couldn't find one from an old multiple choice test, but they do come up. So I just wanted to make sure that we saw at least one of them. So go ahead and see if you can get an answer for that. I will open a poll. There we go. Take another 10 seconds or so. All right, I think we're all in. Perfect. And yeah, crushed it again. Y'all are so going to be so great. So yeah, if we look at this, you can see the answer is B, and you all totally got that right. So here's the work. If we're at the top of the circle, if we're vertical and we're at the top of the circle, the weight and the tension is going to point in the same direction. And so if we plug it in, we know that the sum of the forces, the net force is going to be equal to the tension plus the weight. And then we can just rearrange to get an expression for the tension force. Cool. Last special case before we talk about rotational energy. So sometimes you're going to see curves. You're going to see, usually it's like race cars or things like that going around curves. And there's two different types of curves. So there's unbanked curves and then there's banked curves. And those are exactly what they sound like. A banked curve has it's almost like a ramp that goes in a circle, right? So it's a curve that's on an angle. And it actually allows cars to go faster because it changes up the forces, right? For an unbanked curve, the trick for the unbanked curve is to know that the centripetal force for something turning around an unbanked curve the centripetal force is going to be the friction. So if you look at this free body diagram here, you've got your normal force, you've got your weight, but then the thing pointing towards the center of the circle, if that car is moving, in a circle or turning, is going to be the friction, and the friction is going to act as your centripetal force. For a banked curve, it gets a little bit trickier, but if we look at it, we can see that the horizontal component of the normal force, and if there's friction, if the problem says that there's friction, that's what's going to provide the centripetal force, because the normal force is on an angle. If it's a ramp, right? We can think of it like a ramp that just goes in a circle. If it's on an angle, then we've got that horizontal component that's pointing towards the center of the circle, and that's going to be either in total or part of your centripetal force, depending on if there's friction or not. So it's just good to know that when you see problems like this with the curves, you know where you're looking for the centripetal force, because otherwise, I feel like there's sometimes where you're just like, I don't even know what's going. Like there's so many forces, they're pointing in, I don't even know what direction. So just like knowing that you're looking for friction, and then if it's a banked curve, you're looking for normal force, hopefully is helpful. Okay. In this last bit, we've got like 13 minutes left. Perfect. I have no idea if that's perfect, but we're just going to keep going. So for rotational energy, we've got two ideas here. Rotational kinetic energy generally, and then how it applies to energy conservation. So we've got rotational kinetic energy is a new idea here. And we know that kinetic energy is the energy of motion already. But when an object is spinning, some of its total energy has to go into making it spin. And the name that we give to that energy is called rotational kinetic energy. Formula for it is K for kinetic energy. It's going to be equal to 1/2 I is something called the rotational inertia, or the moment of inertia. You see it's over here. I'll talk about it in a second. And then angular velocity squared. So rotational inertia is basically like mass, but going in a circle. So just like regular inertia is the measure of an object's resistance to moving translationally, rotational inertia is the object's resistance to moving in a circle. And we'll talk about this a lot more in the next cram. So plugging, I think it's next Friday. If you want to know more about rotational inertia, we're going to talk about it a lot. But generally, the idea is if the mass is more spread out, it's further from the axis of rotation, then it's going to have a big rotational inertia. It's going to take a lot to get it to spin. And if the mass is close to the center of the axis of rotation, it's going to have a small rotational inertia. For right now, I'll give you the rotational inertia. We'll just plug it in as I. Again, we'll talk about how to calculate it more in the next cram. Conservation of energy still totally holds, absolutely. Just as a reminder, the idea behind conservation of energy is that assuming there's only conservative forces, there's no friction, there's no air resistance, something like that, then the total energy of the system is always going to stay the same. The only nuance now, the only complexity that we're adding is that the kinetic energy that we talked about in the energy, we talked about all of this in the energy cram, right? But the kinetic energy part now has to do both with the translational kinetic energy, moving in a line, and the rotational kinetic energy. So if we added up both of those plus any change in potential energy, that will get us to 0. Okay, so here we go. Free response question from 2017, so not that long ago. We are actually going to be able to do all 4 parts of this. Actually, it might even be 5 in the next few minutes. So you're not going to work through all of it because we definitely don't have time, but I do want to ask you a little bit about kind of how you would approach it, and then I'll talk through how I would go about answering it in order to kind of give you an example to work off of. So just to unpack it a little bit, we've got this solid cylinder. We know its mass, we know its radius. It's released from rest. It rolls without slipping. So that's telling us that it's rolling as it's going down the ramp, down a 1 meter long inclined plane, and then it's launched horizontally onto the floor. So we've got also like the angle of the ramp and the distance that it falls away. And we also know the rotational inertia. It tells us mr squared over 2. So the first question here asks us to calculate the total kinetic energy of the cylinder as it reaches the horizontal table. So as it reaches the table here, what's the total kinetic energy of the cylinder? And I think I have a question. Yeah, so like I said, I'm not going to have you go through and do all of the math here, even though we will talk about it in a second. But first, just think about, for this first one, as you're looking for the total kinetic energy as it hits the table, what relationship or what like big idea should you use to figure that out? So I have a poll here again. Are we thinking we should be using conservation of momentum, conservation of energy, Newton's second law, centripetal force? Where would you start? What direction would you go if you were going to try to answer this question? And if you don't know, that's totally okay too. I'm going to talk about it. All right, we've got some votes in. Take another couple moments if you're going to take a vote. All right. Great. So for those that voted, which I think now is everyone, great. Y'all got it. We're talking conservation of energy, right? So that's absolutely how we should go about solving this problem. So I will walk you through what I did. First thing, unpack what we know, right? So we've got some info here about what's going on at the top of the ramp, what's going on at the bottom of the ramp. We know the angle of the ramp. That gives us the height of the ramp, and we know the rotational inertia. We also know that energy is conserved from top to bottom, and it asks us to find the total kinetic energy. So that's translational plus rotational at the bottom of the ramp. So that's just straight up conservation of energy. So this isn't even the new stuff yet, right? This is back to just straight conservation of energy. We know that the initial potential energy starts at rest must be equal to the kinetic energy at the bottom of the ramp. Assuming our height there, we'll call that 0 to figure it out, right? So all we do is plug in our potential and kinetic energy equations, solve for kinetic energy, and get 2.45 joules. If we look here, you get 2 points right away for just being able to do that, right? So this is not even any rotation stuff yet, just being able to recognize that we need to do conservation of energy to figure out the kinetic energy at the bottom, and then getting the right answer and including those joules units. So B here says we want to calculate the angular velocity of the cylinder around its axis at the moment it reaches the floor. Okay, so this one is definitely where we need to start thinking about the fact that it's rotating, right? It tells us angular velocity, must have to deal with rotation. So I'm just going to talk through it just because we only have about 5 minutes left. And I want to just make sure we have an idea of how we're going to approach this, because there's a couple of tricks in here. So we know a bunch of stuff. We know that the total kinetic energy is going to be the kinetic energy of it moving translationally plus the kinetic energy of it moving rotationally. So to figure it out, we already know from A what the total kinetic energy is, right? And then from there, we're going to just kind of do a little bit of, I think, massage. I don't really like the word massaging, but you kind of like have to like massage the equations to get to the thing that you need. So we know that the translational kinetic energy formula is 1/2 mv squared. We know that the rotational kinetic energy formula is 1/2 I omega squared. And we know that we're looking for that angular velocity. So we want that omega. And then we're kind of going through and we're like, shoot, I have linear velocity here and I don't know anything about linear velocity. but I do know that it's a relationship here, right? So I can plug in for V, I can plug in R times the angular velocity. Using this conversion relationship is a trick. Well, I don't know if it's a trick, it's a tip, right? So frequently when you're looking at these rotation problems, especially when we're talking about rotational kinetic energy, being able to translate between the linear velocity and the angular velocity is going to be really, really helpful. So this is, I feel like, something that people forget all the time. This like very simple relationship is one that people forget exists. So using this to get rid of that linear velocity and look at everything in terms of angular velocity. From there, it's really just a lot of math, right? So I'm plugging in my my radius. I'm plugging in this moment of inertia, rotational inertia I here was given to me in the problem. So I'm just plugging that in. I'm simplifying. I'm plugging in the numbers that I know from the problem. I know the mass, I know the radius, I know I, and then more math, more simplifying, getting down to the angular velocity is 25.6 radians per second. 3 points this one's worth. So if we look at it, you get a point for just recognizing that the kinetic energy is both linear and rotational. We know that because it says it's rolling without slipping. You get a point for plugging in the equations that we did in terms of like plugging in the moment of inertia, plugging in the V equals R times omega equation, and then you get a point for getting the right answer. Okay, C here. Calculate the ratio of the rotational kinetic energy to the total kinetic energy for the cylinder at the moment it reaches the floor. So this is a ratio. So this actually sounds a lot scarier than it is. All we're going to do here is we're going to say, okay, we know that on the floor, the total kinetic energy is going to be equal to the potential energy at the top. And all I want to do is find that ratio between the rotational kinetic energy to the total kinetic energy. We already know the angular velocity. We know all of the m's and the r's, and we know the total kinetic energy. So this is really just being able to look at it and be like, okay, you need a ratio. This is the ratio that you need. And then I'm going to plug in numbers to figure it out. You've got two ways to do it. You could either look at it in terms of finding the total energy here, or doing what we did. We actually did this alternative solution to figure out the difference. And then the last one here, we really are getting short in time, so I'm just going to talk through it. Calculating the horizontal distance d from the floor here. The way we would do it is we'd use projectile motion. So this will now need to be able to translate back to linear velocity. So we know our angular velocity number from part, I think, B. We know the radius. That will give us our linear velocity. And then this is back from unit 1, just straight up horizontal projectile motion, solve for x here. And then you get a couple points for doing that. And there is an E. Great. So for E, we've got a sphere, same mass and radius, now rolled down the same inclined plane. We've got a new rotational inertia. And then all we're going to do is be able to answer total kinetic energy greater than, less than, or equal, rotational kinetic energy greater than, less than, or equal, and then is the distance greater than, less than, or equal. Just because we are getting real short on time, I'm going to show you the answers here. So the total energy has to be the same because it starts with the same height and the same mass. So it has to start with the initial, the same energy to start. And we know energy is conserved. So that has to be the same. The rotational kinetic energy will be less because the rotational inertia is less. To figure that out, you could totally just plug it in and get an answer for that. Or we can look at those equations and be like, it's a smaller number. It must be less. And then lastly, if the sphere's got less rotational kinetic energy, it's got to have more translational kinetic energy because the total energy is the same. So if it's got more translational kinetic energy, it's going to be going faster linearly off of the table, so it's going to go further. Reminder that all of these slides and all of this work is in that resources section for you. So I know that I went through this last part fast, but it is all here for you to read through at your own pace and, do practice and work through it again as you need to. Just to wrap up, for centripetal force questions and all questions, but definitely centripetal force questions, it's helpful to draw a free body diagram, especially if it's one of those special cases like a vertical circle or a curve. Wanted to remind you again, I know I said it a bunch, but remember that centripetal force isn't a different force. It's not like a special force. It's just a different name that we give to forces we already know. As always, list what you know, what you're looking for, draw a picture, take a deep breath. I know we're getting closer and the pressure is starting to, start to feel the heat, but take a deep breath because y'all have been working hard and you can do it. Trivia on next Tuesday. It's Tuesday, I think, today. Next Tuesday at 9 Eastern for Unit 5. And then this next cram, next Friday, the 9th, is the second half of Unit 5. So this trivia kind of splits the difference between the two parts of Unit 5. So in the next cram, we'll talk about rotational statics and dynamics. That's just talking about like forces, but what happens with forces when we're in a circle. And then we'll talk about angular momentum, which is the same deal. It's just momentum, but what happens when we're in a circle. Kristen is going to hop over to Discord if you would like to keep the conversation going. I think y'all did a great job today. The chat was popping, which is great. So if you have any questions, I am definitely around too. And just reach out. Good luck, y'all. Thank you for being here. Have a great night.